This is another circuit to bias the BJT transistor. It is called as collector to base bias circuit. So you can see that from the supply voltage VCC we have a resistor RC, and at this junction you have a resistor RB connected back to the base. So that's why it's called as collector to base resistor biasing for the BJT. So as usual, you have an NPN transistor with the collector, emitter and the base pins. The base emitter junction is forward bias. The base collector junction is reverse bias to set the operating point to bias the transistor in an active region, and the resistor RB and RC are used to set an operating point of the circuit. Now, as the supply voltage is switched on, the current is drawn into the circuit. So this current is called as, let's say, current I, and it gets divided into two branches. So one is called as a IC and one is called as IB. So this current actually is summation of IC plus IB. Therefore, we say that this current I is nothing but IC plus IB, and that IC plus IB is being divided into two parts, IB and IC. Now we apply a KVL into the circuit. So we say that VCC minus the voltage drop across RC minus the voltage drop across RB minus the voltage drop VBE equal to 0. So with this Kirchhoff voltage law, we can know the values of the currents and voltages into this loop of the circuit. So as I said, RB and RC sets an operating point of the circuit. So there are two ways the operating points can be changed, and we see if and how this circuit can be used to stabilize that operating point, because we don't want any variation once the operating point of the circuit is set. So first reason then that an operating point can be changed is due to rise in temperature. So for a fixed VBE, if the temperature of the circuit rises, it means the collector current will start to increase. So if the collector current starts to increase, we know that the collector current is related to the base current with this equation, that is beta times IB. So if the collector current starts to rise, we know that the IB is therefore IC divided by the beta. So beta base current will also start increasing, and that will change the operating point of the circuit due to rise in the temperature. So how this circuit will react? When due to rise in temperature the collector current rises, so this current which is flowing through the resistor RC is increasing, and due to which the voltage drop across the RC rises. So the voltage drop across the RB therefore decreases, because applying the KVL right here tells us that the VRB, which is the voltage across the resistor RB, will go down. So IB is nothing but VRB divided by RB. So if the VRB goes down, the IB will come down. So due to rise in temperature, collector current rises and the base current will also rise, but due to the action of the connecting the resistor RB from this junction to the base, we see that the IB is coming down. So that's the effect of a negative feedback. Second factor, the transistor has beta. If this transistor is replaced from the circuit, it will have another beta. So higher beta will give rise to higher collector current and therefore the higher base current. But due to the action of connecting the resistor RB from the collector to the base, the variations in the beta will also be not able to affect the DC operating point to a larger extent. So that is how this circuit is helping us to stabilize the operating point against the variation in the temperature or in change in the beta of the transistor.